Okay, so let's go through this practice test. So, this first problem gives you the roots to a characteristic equation of some linear homogeneous ODE with constant coefficients of higher order, and our job is to find the general homogeneous solution then. Okay, so we have R1 is equal to 4, and that occurs twice as a root. R2 is equal to 2, and that occurs 4 times as a root. So for our R1, I'll write out my homogeneous solutions that correspond to R1 as Y11. That's the first solution corresponding to R1. And that's going to be e to the 4x. Y12 of x is going to be the next one that corresponds to R1. So x e to the 4x. Y13 of x is going to be x squared e to the 4x. And y14 of x, oh, sorry, I got the wrong one there. This one only has a multiplicity of 2, so I should only have 2 solutions for that one, right? Because k1 is equal to 2. Now, I can do y21, right? So this is the first one corresponding to R2. That's going to be e to the 2x. Y22 is going to be x e to the 2x. Y23 is going to be x squared e to the 2x. And y24 is going to be x cubed e to the 2x. And so we get that many solutions because multiplicity was 4. So now we're ready to write out our general homogeneous solution, which will just be a linear combination of all these. So I'll write it as C1 e to the 4x plus C2 x e to the 4x plus C3 e to the 2x plus C4 x e to the 2x plus C5 x squared e to the 2x plus C6 x cubed. I don't know why I wrote an equal sign there. C6 x cubed e to the 2x. And there's our final answer. Now we'll go on to the next one. We have some complex roots here, right? So they're of the form alpha plus beta I, right? Where we can see that our alpha is going to be equal to 1, and our beta is going to be equal to 2, right? So alpha equals 1, beta equals 2. Okay, and then we have a multiplicity of 2 for this root and a multiplicity of 2 for this root. There's a little bit of a formatting error. This part should be down here where R3 is equal to 2 and K3 equals 3. Okay, so let's do my R1 then, right? I'll let that be my cosine terms. So here's the first solution that corresponds to cosine then. We're going to have e to the alpha x, so e to the x, cosine of beta x, so cosine of 2x. Y12 of x is going to be x e to the x, cosine of 2x, where again, I'm only going to have 2 cosine terms because my multiplicity was 2 there. Y21 of x, that's going to be my first one corresponding to sine. So we're going to have e to the x, sine of 2x. And we're going to have x e to the x, trouble writing here, x e to the x, sine of 2x. There we go. And that's because our multiplicity was 2 right there. So now we're going to R3. We have y31. Our first solution corresponding to R3 is going to be e to the 2x. Y32 of x is going to be x e to the 2x. And then y33 is going to be x squared e to the 2x, where that's because our multiplicity was 3. So our general homogeneous solution will just be a linear combination of all these. So C1 e to the x cosine of 2x plus C2 x e to the x cosine of 2x plus C3 e to the x sine of 2x, and then plus C4 x e to the x sine of 2x plus C5 e to the 2x plus C6 x e to the 2x plus C7 x squared e to the 2x, and that's it. Okay. Now we go on to the last one over here. I'll go ahead and write out some of these solutions. So like y11 of x is going to be e to the 0x, which is 1. Y12 of x is going to be x times the first solution, so it's just going to be x. So that takes care of this root. Okay. For R2 and R3, I'm going to do my cosine term first. So we're going to have y21 of x. It's going to be e to the x cosine of 3x. My y22 of x is going to be x e to the x cosine of 3x. Okay, so that'll be my cosine terms. Now I'll just do my sine terms here. y31 of x is going to be e to the x sine of 3x. And y32 of x is going to be e to the x cosine of 3x. Okay, so that takes care of my sine terms there. And then now I have two more complex roots here over here. So I'll do my cosine terms first. So I'm going to have y4 of x is going to be e to the 3x cosine of x, right? Do my cosine terms first. Since the multiplicity was only one, I didn't have to need to do double subscripts there. So I'll just leave it like that. And then y5 of x will be e to the 3x sine of x. Okay, so it takes care of that one. All right, so then now our general homogeneous solution is just a linear combination of this. C1 times 1, I'll just leave it as C1, plus C2 times x, that's good, plus C3 times e to the x cosine of 3x, plus C4 x e to the x cosine of 3x, plus C5 e to the x sine of 3x, plus C6 x e to the x sine of 3x, plus C7 e to the 3x cosine of x, plus C8 e to the 3x sine of x. All right, there we have it. Now we go on to problem 2, where we're doing method of undetermined coefficients, basically. We're using that theorem to find the form of the particular solution. We're not actually trying to solve for the constants, but we have to find the form of the particular solution. Okay, so here's how we're going to show our work for this one. Our f of x is equal to 7x cubed times plus x squared times e to the 2x. So we have f of x equals 7x cubed plus x squared. There's our polynomial. E to the 2x. There is our exponential function. And then you can do either sine or cosine, but this doesn't have a sine or a cosine here. So we're going to insert cosine of 0x here. Okay, the reason we're inserting cosine of 0x as opposed to sine of 0x is because cosine of 0x is just equal to 1. And we can multiply anything by 1 without changing its value. So there we have it. Okay. Our m is the degree of the polynomial part, right? So this is a third degree polynomial. So I'm going to write m equals 3, right? 7x cubed, so m equals 3. Okay. Our alpha is whatever the constant is in the exponent of e, so that's 2. Our beta is whatever the constant is on the inside of cosine or sine, so that's going to be 0. Okay. And then now we have to do k, right? And just as a reminder, k is the number of times that alpha plus beta times I, which in this case would just be 2 plus 0i, which would just be 2. It's the number of times that 2 is a root to the characteristic equation. So we look at the characteristic equation here, we see R2 is equal to 2. So it is a root to the characteristic equation, and it occurs 4 times. So then k will be equal to 4. Okay, so m, alpha, beta, and k. Now we get down to our set of associated functions, which in general, remember, it starts as x to the k power e to the alpha x cosine of beta x, going all the way up through, keep multiplying by x until we get up to x to the k plus m, e to the alpha x cosine of beta x. And then we get the sine terms as well, right? So we would have x to the k, e to the alpha x sine of beta x. And we keep multiplying by x until we get all the way up to x to the k plus m, e to the alpha x sine of beta x. So this is our set of associated functions, right? But because our beta is equal to 0, this is going to be significantly easier. So plugging in that beta is equal to 0. So yeah, this is purely optional to write this step in. Okay, so this is absolutely necessary. The next step here. So plugging in that beta is equal to 0, right, means cosine of 0 is just going to be equal to 1. So we're just going to get our cosine terms, but it's just going to be 1 everywhere. So our sine terms, though, sine of 0 is just 0. So all of our sine terms are just gone. Okay. So I'll go ahead and plug in things. So k is equal to 4. So we're going to start off at x to the 4th power, or e to the alpha x, that's e to the 2x. And then I already said cosine of 0x is just 1, so we could leave that off. Right, and we're going to keep multiplying by x until we get up to x to the k plus m. So we're going to go all the way up to x to the 7th power. Okay, so x to the 5th, e to the 2x, x to the 6th, e to the 2x, and then x to the 7th, e to the 2x, right? So we're stopping at x to the k plus m. Okay. And just keep in mind here, we will always get m plus 1 cosine terms and m plus 1 sine terms. So here are m plus 1, which is 4 cosine terms, and our sine terms are all 0, so we don't write them down. So now our particular solution is just a linear combination of these, which I'm just going to use a, b, c, and d. So ax to the 4th power e to the 2x plus bx to the 5th power e to the 2x plus c x to the 6th power e to the 2x plus d x to the 7th power e to the 2x, and that's it. Okay. And do the same thing down here, right? So our f of x equals x plus 3 e to the x cosine of 2x. Our m is the degree of the polynomial part, so it's a first degree polynomial, so m is equal to 1. Alpha is equal to the exponent in e here, so it's going to be 1. My beta is the coefficient of cosine here, so that's going to be 2. Okay. And then our k is the number of times that alpha plus beta I, which you might want to write out here, what alpha plus beta I comes out to be. So alpha plus beta I would be 1 plus 2i. So we're looking for the number of times that 1 plus 2i is a root to the characteristic equation, which happens twice. So k is equal to 2. All right. So then in my set of associated functions, I'm going to get sine terms and cosine terms since my beta is not 0, right? Starts off at x to the k power, x squared, e to the alpha x, so e to the x, and then cosine of beta x, so cosine of 2x. And now we just keep multiplying by x until we get up to x to the k plus m. So that would be x to the 3rd power, e to the x, cosine of 2x. Okay, so we only have those 2 cosine terms, right? M plus 1 cosine terms. But now we get the exact same sine terms, right? So just replace all of these with sine now. We get x squared, e to the x, sine of 2x, and x cubed, e to the x, sine of 2x. Okay. And then now that we have that, our particular solution, just a linear combination of these. So ax squared, e to the x, cosine of 2x, plus bx cubed, e to the x, cosine of 2x, plus cx squared, e to the x, sine of 2x, plus dx cubed, e to the x, sine of 2x. And there we have it. So that's problems 1 and 2. All right, so now comes the part where we're actually solving some problems here. We have y double prime minus 2y prime plus y is equal to e to the x. And our step 1 here is just to get the characteristic equation, right? So that would be r squared minus 2r plus 1 equals 0, which we can factor pretty easily here. We get r minus 1 quantity squared is equal to 0, which means that we have only one root. We'll call it r1 is equal to 1, but it has a multiplicity of 2. So y1 of x is going to be equal to e to the x, and y2 of x, our second linearly independent solution, will just be x times e to the x. Okay, and those are our 2 solutions that correspond to r1 there. Our general homogeneous solution then will be c1 e to the x plus c2 x e to the x. Now we go on to step 2 here, right, where now we have to look at the non-homogeneous part of this. We have f of x is equal to e to the x, right? I'm going to say this is, write it this way. I'll write it as 1, our polynomial, times e to the x times, and I'll write this as cosine of 0x. Okay, so now it's a polynomial times an exponential function times cosine of 0x there. All right, so we get that our m, our degree of our polynomial, right? Well, it's a constant function, so our degree is 0, right? 0-degree polynomial, not 1, right? Because if it was a first-degree polynomial, it would be a linear function like ax plus b instead of just a constant. Okay, so m is equal to 0. Our alpha, right, is whatever the coefficient on x is in the exponent of e, which is just 1. And our beta is going to be 0 because it's cosine of 0x there, right? And our k is the number of times that alpha plus beta I, so alpha plus beta I, in this case is just 1 plus 0i, which is just 1. So the number of times that 1 is a root to the characteristic equation. So we look at all of our roots here. We see 1 is a root, and it occurs twice. So our k is equal to 2. Okay, so I'm going to do my set of associated functions here. It starts off at x squared, because it's x to the k power, right? E to the alpha x, that's e to the x, right? cosine of 0x, right? And we're going to go all the way up to x to the k plus m, right? So that's x to the second power, right? But we're already at x to the second power. Okay, so this is going to be our entire set of associated functions there. Okay, which means that our particular solution just looks like x squared e to the x. Not terrible, right? Okay. Now we need to plug these into our differential equation here. So we're going to need the derivatives as well. So we're going to have yp prime of x is going to be equal to 2x e to the x plus x squared e to the x. Not too bad. And then yp double prime of x, got to take the derivative again. So we're going to get a 2e to the x plus a 2x e to the x plus another 2x e to the x, so plus 4x e to the x, and then plus the derivative of e to the x there. So we're going to have x squared e to the x. Okay. Now we plug it back into our differential equation. So it's yp double prime, so that's 2e to the x plus 4x e to the x plus x squared e to the x. Okay. Plus oh, my mistake here. I forgot my constant out front. It should be a times x squared e to the x. So this should be, yeah, let me just redo our derivatives here. Step back in time here. My mistake, everybody. So yp of x is going to be a constant times x squared e to the x. So it's a x squared e to the x. Now when I do my derivatives, right, we're going to have a 2ax e to the x plus an ax squared e to the x, right? We're going to have second derivative is going to be a 2a e to the x plus 4ax e to the x plus an ax squared e to the x. There we go. And then now we plug it back into our differential equation here. Our yp double prime is going to be 2a e to the x plus 4ax e to the x plus ax squared e to the x plus, and then now we have, minus a 2y prime. Okay, so let me do that as a minus sign instead. So minus 2 times yp prime is going to be a 2ax e to the x plus ax squared e to the x. Okay, and then plus y. So we're going to get plus an ax squared e to the x. Okay, and that's all supposed to come out to just be equal to e to the x. I'm just going to divide both sides of the equation by e to the x here, right? Which I can do because e to the x is never equal to 0, right? So if I divide by e to the x, I'm going to get this is just gone, this is 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 gone, and this is gone. Okay. So now simplifying this, right, I'm going to group things together by what their power of x is. I only see a 2a over here, so I'm going to leave it as 2a. I have a 4ax here, but now I have a minus of 4ax here, so they're going to cancel off to give me 0. Okay, and then I have an ax squared here, minus a 2ax squared, but then plus another ax squared, so they're going to cancel off to give me 0. So I just have 2a is going to be equal to 1, which means that a is equal to 1/2. So my particular solution is just 1/2 x squared e to the x, right? Just plugging in what my a is right there. Okay, and it just happened to be that everything canceled off here. It's not always going to happen. Okay, now our step 3 is just write down what our general solution is, right? So we're going to take our homogeneous solution, well, c1 e to the x plus c2 x e to the x, plus our particular solution, 1/2 x squared e to the x. All right, and there's our final answer. Now let's do the same thing but with variation of parameters. Our step 1 is very much the same, right? So I'll just copy over what we had before. R1 is a root once with it happening, R1 equals 1, but it happens twice as a root. And so we had that y1 of x was equal to e to the x, and y2 of x was equal to x e to the x. Now, in general, it doesn't really matter which one you call y1 and which one you call y2. But what's important is once you establish an order on these solutions, you got to stick with that order through the entire problem here in the variation of parameters. Okay. Now, y of x is going to be equal to c1 e to the x plus c2 x e to the x. And I said y of x, but I meant y sub h of x. Okay. Now we're going to use variation of parameters, right? So I'm going to do my U1 formula and everything like that, which means that I need to have not just y1 and y2, but also y1 and y2 prime. So I'm going to copy back down y1 of x is e to the x. So then y1 prime of x will also be e to the x. y2 of x is x e to the x. And y2 prime of x is e to the x plus x e to the x. Okay. Now, our u1 of x is going to be equal to the integral of negative f of x times y2 of x divided by, there's this a2 of x out front over here, which is just a coefficient on y double prime. In this case, it'll just be 1, right? But I'm just writing down the formulas here right now. So we have y1 of x times y2 prime of x minus y1 prime of x times y2 of x. Okay? And we're integrating that with respect to x. So I'm going to take this under the denominator over here. I'm going to kind of simplify that first, okay? So if I take y1 of x times y2 prime of x, right? So y1 of x times y2 prime of x minus y1 prime of x times y2 of x, right? Just as a little aside over here, I'll call this, okay? That's going to be equal to, well, y1 times y2 prime is going to be, well, I'll just go ahead and distribute it here. So I'm going to get an e to the 2x plus x e to the 2x, right? Minus y1 prime times y2 of x. So y1 prime times y2 of x will just be x e to the 2x. I see I do get some cancellation here. This is going to cancel off with this one, right? So this whole thing is just going to be equal to e to the 2x, which is not bad, right? That's not bad at all. Okay, so under here, under the radical over here, that's just e to the 2x. Okay, right, and as I already said over here, my a2 of x is the coefficient on y double prime, which is just 1 in this case. Okay, because we're doing the constant coefficient case, and I usually have that constant being 1. Okay, so then now just plugging everything in, right? I have a negative f of x. F of x was just e to the x times y2 of x, which is x e to the x. Okay, all divided by 1 times e to the 2x. Okay, so that's going to be the integral of, well, this is going to be a negative x e to the 2x over e to the 2x. So I'm going to have some cancellation. So I'm just integrating negative x with respect to x, which is just negative 1/2 x squared. Okay, so that's my u1 of x. Now let's do my u2 of x over here. Okay, and I'll write out the formula for that. It looks very much the same, except up top, instead of a negative, I have a positive f of x times y1 of x. Down below is exactly the same denominator. Okay, so y1 of x, y2 prime of x, minus y1 prime of x times y2 of x dx. And feel free to write this formula on your cheat sheet for the exam. Remember, you get a one-page cheat sheet. Okay, and then now, right, I'm going to just plug everything in here. So it's the integral of, now it's just f of x times y1 of x. So it's e to the x for my f of x times e to the x for my y1 of x. A2 of x is just 1. This thing in the brackets over here is just e to the 2x, right? So that's just going to be the integral of e to the 2x over e to the 2x, right? So that's definitely going to cancel. So I'm just integrating 1 with respect to x, which is just going to give me x. Now, my particular solution, right? The form of my particular solution for variation of parameters is always the same. It's u1 times y1 of x plus u2 times y2 of x. Okay, so I'll go ahead and plug it in. So my u1 of x was negative 1/2 x squared times my y1 of x was e to the x. Okay, plus u2 of x was just x times my y2 of x was x e to the x. Okay. And then now we simplify. So this is going to be a negative 1/2 x squared e to the x plus an x squared e to the x, which is just going to give me a positive 1/2 x squared e to the x. Okay, so that's my particular solution. Okay, so then now on to step 3. My general solution is just my homogeneous solution plus my particular solution. All right, and there we have it. All right, same thing we got for the previous problem, which may not always happen. We may get a slightly different particular solution depending on the problem for variation of parameters. But there we have it. All right, now on to Cauchy-Euler equations, which have a very similar strategy to how we solve the constant coefficient case, except now, of course, we don't have constant coefficients, right? So my a2 of x here is t squared, right? My a1 of x is 2t. Oh, sorry, I'm saying x, but really this is t's right here. So my a2 of t, I'll write it. is t squared. My a1 of t is 2t. And then my a0 of t is negative 2. Okay. All right. So, and this is still my f of t over here. F of t equals t squared. So our step one is to get the auxiliary equation or characteristic equation, whatever you want to call it there, right? I'm going to call it an auxiliary equation. I think it's what they call it in the textbook as well. And it looks like this. Um, it's if this is in the general form, we have something that looks like at squared. Let me write this in a different color. All right. We have something that looks like at squared y double prime plus b times t y prime plus c times y is equal to some function of t. Okay, so that's the general form that a Cauchy-Euler equation comes in. The auxiliary equation uses this a, b, and c that we have here. And so the formula for the auxiliary equation is it's a times r squared, replacing y double prime with r squared, plus b minus a times r to the first power, replacing y prime with r to the first power, plus c times just r to the 0 power, which of course is just 1, so it's just c, um, equals our f of t. Okay. Oh, sorry, equals 0 because we're doing the homogeneous version first. Okay. So this is our auxiliary equation, right? And so we're going to go ahead and plug in our a, b, and c here, right? So here our a would just be 1 because it's 1 times t squared. So this is r squared. B minus a, that would be a 2 minus a 1, which is just a 1 times r. And then plus c, so that's going to be a minus 2 equals 0. Okay, so that's our auxiliary equation. And this thing factors quite nicely here. Okay, so we're going to get R1 is negative 2, R2 is equal to 1. And so our first homogeneous solution is just going to be, well, it's not e to the Rx. Instead, it's t to the R1. So this will be t to the negative second. Okay, y2 of t will be t to the first power. Okay, so then so like I said, very similar strategy. Okay. Now we'll do variation of parameters to get our particular solution here. So our u1 of t will be equal to the integral, right? And I'll write out the formula again. So it's negative f of t times y2 of t, all divided by a2 of t times y1 of t times y2 prime of t minus y1 prime of t times y2 of t dt. Okay, so same formula as before. Okay. Now our y1 of t is t to the negative second power, right? So as a little aside over here, right? Maybe I'll copy that back down. y1 of t is t to the negative second. y2 of t is t to the first, right? And so then y1 prime of t will be negative 2 t to the negative third. Our y2 prime of t will just be equal to 1. Okay. So now I can go ahead and compute that denominator there. Y1 times y2 prime, right? So y1 of t times y2 prime of t minus y1 prime of t times y2 of t is going to be equal to, let's see, so t to the negative second times this, so that's just going to be t to the negative second. And then minus y1 prime, so that's negative 2 t to the negative third times t to the first power, which gives us a negative 2 t to the negative second power. So this is all going to come out to be equal to 3 t to the negative second power, right? Combining these together. Okay. So down here then, right, I'll make a little note here that my a2 of t, remember we said that that was equal to the coefficient on y double prime, which is t squared. Okay. So this is now a t squared here. And then what's underneath the bracket over here that I just computed was 3t to the negative second. Okay. So keep that in mind as I plug these in. So have a negative f of t. So my f of t was t squared. Okay. So a negative t squared times y2 of t. And y2 of t was just t to the first power. Okay. Over our a2 of t was t squared times 3t to the negative second dt. Okay. So we're going to get a little cancellation in the denominator, t squared times t to the negative second. Okay. So it's just a constant. We can factor out the negative 1/3. This is going to be the integral of t cubed dt. So that's going to give me a negative 1/12 t to the 4th power, okay, for my u1 of t. Now let's do my u2 of t, okay. A very similar formula here. I'll go ahead and write it out again. So it's a positive f of t times y1 of t over a2 of t times same denominator. So it's y1 of t times y2 prime of t minus y1 prime of t times y2 of t, right? We're integrating this with respect to t. So our u2 of t is going to be the integral. Our f of t was t squared. Our y1 of t was t to the negative second power, I believe. Let me just double check that. Yeah, t to the negative second power. Okay, over a2 of t, right? So that was going to be a t squared. And then this in the parentheses over here was a 3t to the negative second. So again, we get cancellation. T squared times t to the negative second. T squared times t to the negative second. Okay. And so this is just going to be the integral of 1/3 dt, which is just 1/3 t. Now I'm ready to go ahead and write the form of my particular solution here. So this is part 2. Or sorry, we're already on part 2. The form of my particular solution, right, is always the same for variation of parameters. It's u1 of t times y1 of t plus u2 of t times y2 of t. Okay, so that's just going to be, well, so u1 is negative 1/12 t to the 4th power, but then times y1, which is t to the negative second. Okay, plus our u2 of t was 1/3 t times our y2 of t was just t. So we're going to get that this is a negative 1/12 t to the second power plus a 1/3 t to the second power. So if we combine those together, right, this is a 4/12 minus a 1/12, which is just 3/12, which is just 1/4 t squared then. Okay. Now, oh, I said yh of t, but step 3 is the general homogeneous solution here. So step 3 here, we're going to have y of t is going to be equal to c1 t to the negative second plus c2 t to the 1st power. I don't know if I wrote my general homogeneous solution. I did. Okay, good. Plus my particular solution, which was 1/4 t squared. And there we have it. Okay, so that's the last problem.